Okay, so I find the problem with 7a, b, and c is that they're kind of doing everything conceptually, right? All of 7b is just like talking about a wave function, how we deal with a wave function, how you normalize a wave function, without really telling you where a wave function comes from and what a wave function is useful for. And then 7c tells you what is an operator, how do you use an operator, what are the special restrictions on an operator, without really telling you where we're going to use an operator. So today, I'm going to kind of put that all, we're going to do like some stuff from 7d, and we're going to kind of fold that stuff into, we're going to look at a couple real problems today. So the first thing that we're going to look at, the first thing we're going to consider is just consider a particle moving. We're going to call it a free particle. Now this is kind of a fake problem. This is to say, consider a particle moving through space with no other interactions on it. Nothing interacts with it. That doesn't really happen. But it gives us a place to kind of start thinking about the simplest thing. So in this situation, because we're calling it a free particle, we'd essentially say potential energy is equal to 0. That's what we're saying when we say a free particle. This particle, we're going to treat it like a distributed object, the same thinking that we had from all of those problems we talked about last time. We're going to consider the Hamiltonian, the total energy on this thing is going to be the kinetic energy plus the potential energy. Where we just said, if we're doing a free particle, we can just set the potential energy equal to 0. If we were looking at the kinetic energy of a classical particle, so how you would see it in your typical physics if you were throwing a ball, something like that, you'd say your kinetic energy is equal to 1/2 mv squared. I'm going to do it in one dimension, so I'm going to say velocity along the x direction. That's a lowercase, that's a subscript x there. Or, if we wanted to put it in terms of momentum, we could also write it as 1/2 mp squared. Is everyone comfortable with that? Just as a quick reminder, P is equal to mass times velocity. Again, I'm just putting the x's because we're doing it just in the x direction for now. We'll add extra dimensions in later. So if I put in P twice, P divided by m is going to be V. If I do that twice, I end up with 1m on bottom. Now, if we wanted to do this in a quantum mechanical world, we're going to make use of postulate 2. Do you remember what postulate 2 says? Look it in your notes, say it to your neighbor real quick. What's postulate 2 say? I hope it's postulate 2.
Acting on the function operator in the classical world has a corresponding quantum operation.
So here's our classical thing. Here's our classical thing. There's some operator, right? These equations for the classical is just like throwing a ball, throwing a single object. If we wanted it to be a distributed object, a quantum object, we have to use some different thing for this. And that different thing we're going to use, I'm just going to kind of tell you what it is. To denote something as an operator, we give it a little hat. And we would call this, when we talk about this, this would be px hat, or the momentum operator in the x direction. I like saying px hat. So this operator has a particular equation, a particular mathematical operation associated with it. And that's it. Normally, we would not see it by itself. We would typically see it as the px hat operator operating on a function, giving us negative I h bar d by dx on that function. Right? That would be the definition of how we think about if we've got a momentum operator, just writing the operator like this, right, having the derivative with respect to x just hanging out there doesn't make a lot of sense. It has to be operating on something for it to really make sense. Now the big question, something that's kind of funny that you might ask is, well, why is it there this negative IH bar? We're going to put an additional restriction on postulate 2. So the other thing that we're going to see here is when we do this operation, the observables that we see, what color going? We'll keep going with green. Right, this is going to be postulate 3. Postulate 3 tells us there's only certain allowed values for the momentum. And so that's going to be, if I have this momentum operator operating on a wave function, I'm going to get some momentum values and that wave function back. Putting some labels on this, that's our operator. That is possible value. And that is, both of these are the wave function. So if we wanted to know the momentum of this particle, we've got a particle flying through space. It's all kinetic energy, and we want to figure out, well, how fast is it moving? What's the momentum of this particle? I would take the momentum operator, operate on the wave function for the particle. That would get me a momentum value times the wave function. We use some special language. It turns out problems that are set up like this, where it's operator on a function gives a single value and the function back, this whole thing has a special name. This is called an eigenvalue problem. And so what we're going to be solving this quarter is we're going to be solving eigenvalue problems, where this possible value is called an eigenvalue. This operator we're using would be called an eigenoperator. And this function we're using would be called an eigenfunction. Now, the mathematics of eigenvalue problems go way beyond quantum mechanics. They're used in all kinds of places. We are going to be using it particularly here in quantum mechanics for this third postulate to get these possible values, where essentially we have to return the same function back. And if you're thinking about this a little bit, you'll notice this that comes out of the third postulate. This is some of the math we did right at the end of class last time for solving differential equations. We've got our differential here. We've got it operating on something. So we're going to be able to figure out our functions. Now, why the IH? Why the negative I there? More vocabulary. Let's see here. We're going to modify postulate 2 right? We want our operator, and in fact, we want all of our operators in quantum mechanics to be Hermitian operators. What the heck does that mean? Right now, it might not mean anything, but essentially, if we're doing this type of operation and we get possible values, can momentum be imaginary? We need the momentum to be real. And so there's two possibilities for the way that we guarantee real momentums here. One is we can put some arbitrary restrictions on our wave function, or we can put some restrictions on our operator. Sometimes we'll do both, but it turns out more realistically, postulate 2 says not only do you need a corresponding operator in quantum mechanics, it needs to be a Hermitian operator and it needs to be a linear operator. This will guarantee that we get real values. So what's that look like? Doing the weird things still. So let's look at something generic real quick. Let's go back to this. If we're looking at a generic eigenvalue problem, we're going to have a hat operating on some function, giving us some value a and the function back. Right? We've got a hat operating on psi, giving us the value a and the function psi. So this needs to be a value. A can't be part of a function. It's just a value. It's some number. If we wanted this to be real, essentially what I'm saying is a has to be equal to a star. That is to say, this is one way to talk about things being real. The only way that we can have a equal to a star is if there's no imaginary part to a. So that is to say, if a is a real number, taking the complex conjugate of a real number is just that real number again. So this is one way that we can guarantee it. In quantum mechanics, the way we usually write it, so we can do a little bit of different math with it, we'll also look at it in terms of the average value of a is equal to the average value of a star. Now the reason we do it this way is because there's some different calculations we can do for a Hermitian operator. So then the question becomes, what's this weird a in the angled brackets mean? This actually, part of this comes from postulate 1. So from the interpretation of postulate 1, we could essentially say there is some way to calculate this average value of a. There's a couple different ways we talk about it. We can call this the average value or the expectation value. And the way we write this down is going to be from postulate 4. So postulate 4 says the expectation value of some operator a is going to be the integral right, so that's going to get us the expectation value, the average value of a, is going to be defined by this psi star a psi d tau, this integral over all space. Again, I'm doing this generically, so I'm not doing this sub x's. We'll get back to that in just a moment. Now, we can do a couple things here, right? I've got this definition of the eigenvalue problem, so I can rewrite this. I can rewrite this chunk as a psi, using this definition over here. Good so far? What this means is my angled brackets a over all space is going to be equal to a times psi star psi d tau. Since a is just a constant, it's just some number, I can move that bit outside of the integral. And this chunk here right, that's the definition of probability from that first postulate again, right? That interpretation of the first postulate says we've got some probability times some measurement if we take the probability over all space. So looking at, everywhere we've got a probability in some value of A, we get some average value of what that A is going to be. Now, if we want to guarantee realness, the fact that this is a Hermitian operator, the way we would write this down, let's see. Right? If we want to guarantee that our expectation values are, that our eigenvalues, our possible values that we're going to measure are real, we're going to essentially end up with this thing, A star. So I'm going to have the integral of psi star A hat psi d tau is equal to integral psi star A hat psi d tau star. Again, this is all generically. This is the definition of what it means to be a Hermitian. That hat looks funny. Let's fix that hat. Right? This is the definition of what it means to be a Hermitian. If you get this expectation value, or if you take the complex conjugate of the expectation value, they're the same thing. Right? We're not going to have to do this quarter very often. Right? Most of the time when we're looking at our operators, I'm just going to do this thing where I'm like, hey, here's the operator. It's already Hermitian. I'm not going to ask you to prove that it's Hermitian. Question?
When you say it's complex conjugate, you just mean there's no imaginary part to it?
Right.
So
but
okay.
If you remember, our wave functions could have imaginary parts.
Yeah.
Our operators could have imaginary parts. But our measurements and our expectation values can't have imaginary parts. So how do we guarantee that happens? We formulate the operators properly so that they are Hermitian. And an operator, so this whole thing is, let's see, how can you do this? Let's see this. Right? So the idea here is, for this thing to be true, for this back and forth to be true, only particular operators are going to work. So why did I put an IH, why did I put this negative I out front of the derivative? Because that's going to make it so this works. Right? And I didn't put it there, but why that negative I is there is to guarantee that the operator is Hermitian. That's going to do two things for us. Having Hermitian operators does two really nice things for us. The first thing it does is it guarantees that our values are real. So our eigenvalues of Hermitian operators will be real. That means as long as the operators we're using in quantum mechanics are this special condition to be a Hermitian operator, the possible values are going to be real values. That's a good thing. The second thing it's going to do. Wait, was that a question? Or?
Yeah.
Yeah.
So I understand that you need that to make the values Hermitian, but where are they coming from?
Which part?
The I and the H.
So essentially, it's a pretty roundabout way for deriving the momentum operator. Essentially, you have functions that describe a wave that's moving through space, and then you try to take the momentum, you try to get the expectation value of the momentum, and if you just did it with the d by dx for finding the momentum, you would not have a Hermitian operator. And there's a couple different ways you can do it. If you plug everything in and solve it around, you get an extra value of I minus, you get like a negative I left over. And so you just say, oh, I must need that in my operator in order to make it Hermitian. So there was actually quite a process in order to generate this operator and figure out what it was. I never had to do it.
Kind of trial by error, we're figuring this out and not getting it, but it looks like there's very specific values that we're missing.
Yeah. So if you tried to do this with a non-Hermitian operator, these two things are not equal to each other, and they're off by some value. And you can, if you're able to modify your operator by putting that value in, like a negative I, then you can force your operator to be Hermitian. So they forced the operator is forced to be Hermitian by putting that negative I in there. Question over here and then over there.
Could you think about it, how like some equations have constants kind of included in them?
Yeah.
So that the numbers are down. Does that sound?
Yeah, so there's a constant in there. It's weird because this constant is I, right? It's the square root of -1. But that constant in there is going to make it so we end up with real values. Question here, and then I've got a question for all of you. What's your question?
So is it when you set up the integrals, like you have to keep like a hat inside the integral, but then the little a can take it out?
Correct, because a hat, remember, a hat's an operator, and we need it to be with a function. Right, so just like p hat doesn't really make sense by itself, a hat needs to be on a function. But after it operates on that function, we just get a constant value out times that function again if it's an eigenfunction getting an eigenvalue. So within our context of our problem. Question back there, yeah.
We said that the operator has to be linear too.
Yes.
What does that mean?
We'll get to that in a little bit later. That's something that'll come up probably next class. I threw it in there now, but we haven't shown that it's linear yet. Question, yeah.
Also, where did the one rho squared over 2m go? Are we assuming that that is the wave function? Is that what?
Wait, which part?
The classical, like.
Classical.
I
So.
understand that it's classical, but like the quantum analog of that.
So which part are you talking about? Which part went away? So this is the momentum operator, not the kinetic energy operator. So when we get the kinetic energy, let's do the, ooh, that's the next thing I was going to do, but I'll just do it now. When we look at, I'll do it here. I'll do it here. When we look at the kinetic energy operator, that's going to be negative h bar squared over 2m d by dx squared. Or we could look at that if we wanted to look at it a little bit simpler. That would be 1 over 2m px hat squared. I should have done that in the other order. Right, so when we go to the kinetic energy operator, rather than just the kinetic energy, we actually get the same thing, 1 over 2m momentum squared. But that momentum squared, now instead of just being a value, is an operator. Is that the part that was missing, was the 2m? We'll get to a problem, okay? So again, we're not going to often have to prove that operators are Hermitian. We're usually just going to have an operator that is Hermitian, and then we're going to work with it. So if we wanted to, we could take 10 minutes right now, and we could take the momentum operator, we could plug it in here, we could get some test function, use some function, and we could prove that it's a Hermitian operator. But we'll have to get a function that's an eigenfunction first. Question?
What is the second nice thing about Hermitian operators aside from that they...
Yeah, I didn't get to the second nice thing, did I? The second nice thing is that the functions of a Hermitian operator, the eigenfunctions of a Hermitian operator, are going to be orthogonal to each other. Now, if you remember back from the first day, orthogonal axis systems were nice, right? Our x and our y being 90 degrees away from each other made it so we could separate problems into the x part and the y part. Having functions that are orthogonal to each other are going to do the same thing. They're going to let us start splitting the problem up. It's also going to be really nice when we do integrals, because if we have two things that are orthogonal to each other, they don't overlap at all. So their integral is 0. And we'll see some examples of that. If we've got time, we'll see some examples of that today. I'm hoping we get to that today. That's my hope. Question back there, yeah.
What's the difference between the A, the lowercase a, and the average value?
So the lowercase a is one of the possible. You remember the dice thing where we had a lot of different possibilities? You could roll 2, 3, 4, 5, 6, 7. The lowercase a is like that. It's the 2, the 3, the 4, the 5, and it's the different possible values. The brackets a is if we take the average of all of those. And so this is an average. So that's where we've got the probability of a measurement times that measurement gets us the average. Right? So it's average value versus many particular possible values.
And it's all with the same operator? Or
Yeah, so this would be looking at the same operator, right? So we can look at this in terms of momentum. Should we look at what happens with the free particle with momentum? Okay, let's do that. So I'm going to leave that stuff up. I was trying to decide what to erase. Here's what I'm going to erase. I'm going to erase this stuff over here. I'm going to rewrite that in just a moment. Leave that there. So if we have a free particle, if you remember, there's certain steps we always take for solving a problem. Here, what we're going to do is we're going to solve the time-independent Schrödinger equation. Which is going to get us the total energy. So what that's going to do is that's going to say, hey, if I take my Hamiltonian operator on some wave function, I will get the energy out and the same wave function back. Where again, that energy is going to be a numerical value. It's going to be some number, and it's going to be some possible energy we could measure in our system. And the first step we do is after we define our system, so here's our system defined. We're doing a free particle. We've got kinetic energy, no potential energy. If we've got kinetic energy and no potential energy, our Hamiltonian operator is going to be 1 over 2m px hat. That's our momentum operator. If we operate on a function, well, first let's rewrite that with our definition of what px is. I just erased it, but if you remember, px hat is negative I h bar d by dx. So if I take, whoa, sorry, forgot to square that. Momentum squared. Momentum squared. So if I square this, I'm going to have my Hamiltonian operator equal to negative I h bar d by dx squared divided by 2m. Now, most of this is pretty easy to do. Oh, that's what I was going to ask. 1 through 5, comfort with imaginary numbers and complex conjugates. Oh, okay. Whoa. That was a lot more zeros and ones than I was expecting. So, a couple things. I is equal to the square root of negative 1. I squared is equal to negative 1. I cubed is going to be equal to negative I, which is equal to negative square root of negative 1. I to the 4th is just equal to 1. Now, another funny thing that happens, can I remember the funny thing that happens? What's the other useful one? over, I can't remember the other useful one right now. It'll come to me. It was in the textbook. It's some of the videos you find, instead of using negative, oh, that's what it is, negative I equals 1 over I. Some of the videos you'll find, they use a slight different definition for the momentum operator, where instead of negative I, they use 1 over I, if memory serves. And I think those two things end up equal to each other. Is that right?
It uses h bar over I for the momentum operator.
What is that?
The book uses h bar over I for the momentum operator instead of negative I.
Oh, right.
H bar.
Okay, so if you have
They're the same thing.
1 over I ends up being equal to negative I. How is that possible? Well, if you take 1 over I and you multiply by I over I, you get an I on top and a negative 1 on bottom. That's negative I. So it's this kind of weird trick that you see every once in a while. Right, so this chunk ends up being I over negative 1, which is equal to negative I. So you'll see things flipped that way every once in a while. Don't be scared by it. This is a weird math trick. Some people find it easier to write 1 over I instead of writing negative I. And so depending on which book you're looking in or which video you're watching, you'll see it done different ways. It's all equivalent to each other. I guess the other thing I should tell you real quick, and please read this in the textbook as well, if you had like A plus, let me do it with lowercase things, A plus IB, and then you take, well, how do I want to write this down? If you took the complex conjugate of A plus IB, that's equal to A minus IB. So all that happens when you take the complex conjugate is you flip the sign of your imaginary portions. Your positive imaginary becomes a negative imaginary. Now, this does not work for, if this was real, if I just had A and I took the complex conjugate, I'd still just have A. If there's no imaginary part, taking the complex conjugate does nothing. Which is why this requirement guarantees that it's real. Because the only way taking the complex conjugate gives you the exact same value back is if there's no imaginary part in there. I should have asked about how good you were with imaginary and complex conjugates before I did all that. I'm sorry. Okay, so when I end up with negative I squared, the negative just becomes positive. I squared becomes a minus 1. So this Hamiltonian operator ends up being negative h bar squared over 2m d by dx squared. I got rid of my imaginary part. I end up with a negative out front, but that imaginary part isn't there anymore. Kind of nice. Now what we have to do, we still don't know what these wave functions are though. So the next step in this, we've got our problem defined, we've got our kinetic energy, everything is kinetic energy, no potential energy. Now what I need to do is I need to solve h psi equals E psi. That Schrodinger equation. Where I'm just going to plug in what h is equal to. This is equal to negative h bar squared over 2m d by dx squared. And now I feel foolish for not putting this in explicitly before. Our wave functions are functions of x. Oh, other thing. Y'all know what h bar is? No. Read the textbook. So h bar is Planck's constant divided by 2 pi. It's called the reduced Planck's constant. So it turns out in a lot of stuff we do, we keep ending up with these 2 pi's everywhere, and so we just call it h bar. It's just a constant. It's a constant that becomes really important on the quantum scale because this quantization of energy happens at this numerical value, 6.626 times 10 to the negative 34 joules seconds. Right? If you've got energy on that really, really, really small scale, then these quantum effects start to become measurable. That's part of why we don't see quantum effects on the human scale, the energies are all too large. Right? This is also what was happening in the black body radiation, or Einstein's heat capacity, where if you were at high energies, this quantum stuff didn't really matter. Classical does fine. But at low energies, this quantum stuff starts to matter. And the scale at which that happens is related to Planck's constant. So it's just a constant. That's part of why I forgot about it. It's also like, once you do this stuff enough, you're just like, oh yeah, h-bars are everywhere. So h-bars everywhere, it's just a constant. I could have just written a number there, but the number is 6.626 times 10 to the negative 34 divided by 2 pi, and it just gets really exhausting to write it over and over again. Question?
Why did it go from a double derivative to a single?
Oh, because I didn't finish. I got distracted by h-bar. Should still be a double derivatives. Thank you for catching that. Same thing? Oh, a different question? I thought I saw another hand.
It was the same.
Same thing. Okay, great. So I'm going to rearrange things a little bit to try and make this look like a problem we've seen before. What I'm going to do is I'm going to multiply by the 2m, divide by the negative h-bar squared. And I'm going to rewrite this so I've got d by dx squared of psi of x is equal to negative 2me over h bar squared psi of x. Then I'm going to do one more thing. I'm going to call this whole chunk k squared 2me over h bar squared. And the reason I do that is so I can write this down as d by dx squared psi is equal to negative k squared psi. Right? And this is the problem we did at the end of class last time. That's a simple, okay, I'm going to call it simple, but you know, the word simple is always a trap. That's a simple differential equation. Do we remember the solutions we had for that simple differential equation? Everyone okay if I erase this board? Okay. Question? Or you remember the answers? What were some of the, give me one of the possible answers.
Cosine.
Yep, that's one. Someone else, someone have another one? What's the other one?
E to the negative kx by kx.
And what's the other one?
0. Oh.
E to the ikx also works. 0, boring. Zero's a boring answer. Right, so we've got these possibilities. Right, so we've got these possible values for our wave functions. Some of these wave functions work in some cases. Some of them work in other cases. Would you all be surprised if I told you these were all the same thing? We'll get there. We'll get there. We'll get there. Do you want to know why? I'll say something and you'll all groan. It's Euler's equation, Taylor series expansions. And Taylor series expansions makes it so all of these things can relate to each other. It's the Euler decomposition or Euler's equation. Okay. Let's see, where am I in my notes now? Okay, so we've got all these. We could also do multiples of k. This could be cosine of 2kx, cosine of 3kx, cosine of 4kx. All of those would still work. You just have an extra constant up front. Now we can go ahead. I'm just going to pick one, and we're going to work with that one to start. We could pick any of them, but I'm going to pick e to the ikx to try. And now I'm going to ask, what are the different things I can figure out about the momentum? Here's a possible wave function. Let me write this a little bit differently. Psi of x is equal to e to the ikx, right? So I'm going to try this function. And I'm going to see what I can tell about this. This is one of the possible answers. This is one of the eigenfunctions for the Hamiltonian operator. A Hamiltonian operator is a Hermitian operator, so I should get real values for this. Even though it's an imaginary function, I should get real values for momentum. So let's start with just looking at that. Let's figure out what's the possible momentum. So I'm going to go ahead and I'm going to do p hat of x on psi of x is equal to, I want to make this look like a lowercase p. P of x, psi of x. Plug in my, psi as a function of x. So plug in my different things. I've got negative I h bar d by dx of e to the I k x equal to some momentum value times e to the I k x. Now I can't just divide over, right? Because I have to take this derivative before I do any division or multiplication or anything. If I take if I take the derivative of e to the I k x, this should give me I k e to the I k x. Does everyone agree with that? 1 through 5, memory of derivatives. We're really just going to be doing a couple things. We're going to be doing x. We're really just going to be working with these functions most of the time, or things related to these functions most of the time. It will get a little bit more complicated as we get to more complicated problems, but for now, this is what we got. Okay, now I've got to do a little bit more, so I'm going to have, this is going to look weird, I'm going to have negative I times I h bar k times e to the I k x equal to px e to the I k x. Now that I've done the derivative, now I can get rid of that function, and I can figure out what my momentum is equal to. Negative I times I, that would be 1. I'm just going to get h bar k is equal to px. Now, that possible value, h bar k, right now you look at that and you're like, great, well, what's that matter? Remember, k has some meaning now. When we were over here, we have k squared is equal to 2me over h bar squared. K is related to the energy. So I can plug that k value back in, and I can get h bar times the square root of 2me over h bar squared equals p of x, right? Because that k has a value that we've defined. I just took the square root to simplify it. Notice that h bar is going to cancel out, and my momentum is going to be related to the energy. That's all we get. The momentum is related to the energy divided by 2 times the mass. We get kind of the classical result back. We get, I erased it. Can't point at it. But we're going to get px over 2m. Right? We're going to get something related back to the original idea of kinetic energy. And that should make sense, because we only have kinetic energy in this problem. If kinetic energy is the only thing we have, then all the energy is related to the momentum. So we haven't done much here. We did some operations, we've done some quantum mechanics, and we've pretty much said all of the energy is kinetic energy. Now, but we did it on a quantum object rather than a classical object. Now, we run into a problem if we wanted to find, let's do another thing. So this was finding momentum. We could go ahead and say, okay, well now, let's find something else. Let's find the position. The position operator. This is not going to work, just to let you know. We're going to run into some problems with this. So now we can say, okay, well, let's go ahead and find the position of a particle that could be anywhere in the universe. You can see why this is going to be a problem, right? The particle can be anywhere in the universe because it's a free particle. Can kind of be anywhere in the universe. But let's see how this comes out. So the position operator in quantum mechanics is just multiplied by x. So the position operator is multiplied by x. So if I want to find x hat on my psi of x equal to some x value, I'm going to call it x value. I feel like I should put the x in quotes, right? This is kind of weird. I don't know what to call this thing. I had this problem in my notes as well. Right? I need a variable here that's just like a number related to x. Can I call it a of x? Is that okay with everyone? Sure. So it's a number related to the position and the psi of x factor. Now, here's where we run into our first problem with this. If you look at this, if I plug in my definition of x hat, if I plug in all of my definitions here, I'm going to have x times e to the ikx is equal to a of x e to the ikx. Are those functions the same? This is a problem. This is not actually an eigenvalue problem. Operating with x is going to change our function such that we really can't say something about the individual position measurements in terms of these functions. So we switch and we say, okay, well, if we can't say the individual values we might get, can we say something about the average value? So what about average position? Can we say something definitive about average position here? So what we're going to do is we're just going to write it down. We're going to say, okay, average position is going to be equal to the integral of psi of x star x hat psi of x. And I can switch my d tau to dx because now I'm doing one dimension again. So I'm just going to integrate over x because I'm in one dimension. I can plug in my definition, the function I'm trying, and my x operator. And oh, this is over all space. So negative infinity to positive infinity. My average position is going to be the integral of e. Okay, I'm going to do something a little bit funny. Since we had some people who need practice with complex conjugates, I'm going to have the complex conjugate of my wave function. What's that going to do? It's going to flip the sign of that I to just be a negative I. So I'm going to have e to the minus ikx, e to the ikx times x. This exponential times that exponential times x. Those exponentials disappear. We run into another problem. If we tried to do this integral over all space, we get some like infinite answer. We get negative infinity to positive infinity. It could be infinitely anywhere. Now, this is because of the thing that I said right at the beginning, where I said, look, the free particle problem is not a realistic problem because you never have a particle that's interacting with nothing. So there's two different tricks that people use to try and make particles look more realistic. The first trick people use is using what's called a wave packet function. So instead of just using an e to the ikx, they use like several cosines and sines put together. They make a more complicated function, and then that complicated function is localized in one place in space because of the way that the different cosines and sines combine with each other. That's an option. That's called making a wave packet. It's really cool. It does a lot of interesting things in physics, is not as useful in a chemistry class because we don't often deal with particles flying off nowhere, right? We usually deal with particles bound to something, like an electron stuck around a nucleus or an electron stuck across a molecule. So we're going to use the second method for making this more realistic and limiting all of our space. Instead of doing all space, we're going to say, what if the particle was just trapped between 0 and L? It was trapped in some box. And if it's trapped in that space, then we can actually do some integrals and make some sense out of what's happening in that space. If we try to do it over all space, it gets to be a mess. So let's go ahead and look at what a particle looks like if it's trapped in a particular spot in space. Question?
Before we move on, can you explain why that's not even
So x e to the ikx, this is a different function. Right, x e times e to the ikx. If we plotted on an axis of like x and value, this side would have a different equation than this side. Since the equations don't match, since it's not the same mathematical function on both sides, it's not an eigenvalue problem. We've done something weird. This is a non-eigenvalue problem. We can still do some things. We'll find we can still do some things when we don't have the eigenvalue problems, but we can't get the individual measurements, the individual possible values. Other questions? While I erase this board, is it okay if I erase this board? Question?
I'm sure it's simple math, but how do the e negative ikx and e ikx cancel out?
When you have two exponentials times each other, you add their powers.
Right.
So you're just going to have like ikx minus ikx, and you end up with e to the 0, which is equal to 1. Question?
I have a question about this board.
Ooh. Okay. I didn't mean to throw it that dramatic. That was an accident.
It's like h hat equals negative I blah blah squared.
Yeah.
Why does the negative remain?
So remember, it's negative I, so the negative squared is equal to 1, but I squared is equal to negative 1.
Okay. Yeah,
Right.
okay, yeah, that makes sense.
You got it? You got it? Okay. Question back there?
I know it was erased, but for finding momentum, when we included K,
Mm-hmm.
would we not been able to define K if we hadn't done that work there?
Yes, right. We needed to do this work here. Remember that finding the momentum was in terms of the Hamiltonian operator. So we needed to have K defined in terms of the actual energy of the system in order to do all of that work. And the only reason I do that is because it's a lot easier to solve this equation than it is to solve this equation. Like, I just see this and I'm like, okay, I can think of how to write down equations for this one. This one, we could have left it like this the entire time and just been writing square root of 2me over h bar squared the entire time. It's just cumbersome. We'll just try to find some shortcuts. Question over here, and then we'll get you a second one. Yeah.
I'm sorry. I guess I'm confused, like, why the dx is not sensible for all space. Like, should that be like dx, dy, dz? Oh, for the average position.
It's the average position. It's not just the dx. It's integrating. If we do this from negative infinity, so x is going to give us like a x squared over 2 from negative infinity to positive infinity. You just end up with infinity.
Oh, okay.
Right. So we're not doing like a generic integral. We're doing an integral over bounds from negative infinity to positive infinity. And so if we do x squared from negative infinity to positive infinity, you get infinity minus infinity or infinity plus infinity, something like that. You get weird stuff that doesn't really make sense. And it's okay that it doesn't make sense because we kind of started with a concept that wasn't totally reasonable. Other questions? Okay. So, to get something more reasonable, we're finally going to do something that's a realistic problem. And this problem of a particle in a box can actually be applied to systems in chemistry that you've dealt with before. So, a particle in a box, my favorite example of it, I'll just tell you now what my favorite example of it is, and once we solve all of this, we can look at some calculations with this. But a particle in a box would be like having an electron in a conjugated pi system. that can move back and forth along a chain of like p orbitals. Do all of those words make sense? Conjugated pi system? Right. So you know those have optical properties, right? If you look at my favorite example of this, I did this in my undergrad, and I was just like, whoa. Beta carotene. What color is beta carotene?
Orange.
It's orange. Why is it orange? It absorbs blue light. Why does it absorb blue light? You can treat it like electrons stuck in a box, traveling up and down the conjugated pi system, and the energy gap happens to be blue light. So particle in a box can actually be applied to conjugated pi systems to understand the energy levels of conjugated pi systems. Linear conjugated pi systems. If we wanted to do rings, we have to do a two-dimensional box. And we're going to do that. But if we're doing a one-dimensional, it's just going to be like a linear conjugated pi system. We'll do rings and other things like that later. By later, I mean next week. So particle in a box. We'll see how far we get through this today. Often abbreviated, ooh, that's not how you write B. Often abbreviated just the PIB problem. We're going to start with saying, okay, so I've got some container that goes from 0 to L. It's got some length to it. Over here, it goes off to infinity. So over here, we've got nothing. Over here, we've got nothing. And this is on the energy scale. So if this is like energy this direction. Let's see. I had a nice way I wrote this down. Okay, here we go. I'm just going to write it down. From negative infinity to 0, our potential is equal to infinity. So essentially, it takes so much energy to get out of the box, the particle can never escape. Inside the box, our potential is 0, kind of like the free particle system we had. On the other side of the box, our potential is, again, infinity. Oh, sorry. Yeah, no, infinity. So, essentially, if we had a particle trapped in here, it's stuck. If we wanted to push it past L, it would take an infinite amount of energy to push it out of the box that way. Do we have an infinite amount of energy? Nope, it's stuck there. If we wanted to push it past 0 to some negative distance, we'd have to push it with an infinite amount of energy. So again, this is kind of a fictional restriction on it. It's approximately true for a lot of systems. So the particle in the box becomes a pretty reasonable representation of some problems we see in chemistry. So let's go ahead and set this up. Inside the box, 0 potential, we end up with stuff that looks really familiar to the same stuff we just did. So inside the box, we're going to have h hat on psi of x. The wave functions for this might be different than the other ones we just did. Equals E psi of x, right? We always kind of start with the Hamiltonian equation. The thing that makes our problems different is how we define the Hamiltonian. Right? The Hamiltonian is going to be negative h bar squared over 2m d by d. Well, let me write this a little bit, sorry. 1 over 2m p of x hat squared plus v of x, some potential. This means for us, now I'll write the thing I was about to write, that means we're almost always going to have negative h bar squared over 2m d by dx squared plus some v, some potential energy. Question?
When you're, oh, sorry, you just said potential energy, okay.
Yeah.
You're just denoting that as V.
Yeah.
Okay. Thank you.
Right, that's our potential energy, some value. For the particle in a box, we're doing a flat box. No potential across it. There's a lot of modifications we can do this to make it look more like a molecule. We could put some ridges, we could put some slopes, things like that, but we're just doing the simplest one first. Is that okay? Okay. 'Cause even the simplest one gets kind of weird. So if that's our operator, I'm going to go ahead and do this again. I'm going to set up the same type of thing. I'm going to have negative h bar squared over 2m d by dx squared on my psi of x. I don't know my size yet because this is a different problem. Is equal to e psi of x. I don't know my size yet, but you all see how it's kind of the same problem already? We're going to get the same possible functions. I'm going to rearrange this again the same way I did the other one. D by dx squared psi of x is equal to negative 2me on h bar squared psi of x. I'm again going to define this whole chunk as k squared equals 2me on h bar squared. And guess what? Same possible functions. Could be a cosine, could be a sine, could be an e to the ix, e to the minus ix. Same possible functions come out. So why aren't we stuck in the exact same problem we had before, where we end up in nonsense values? Yeah.
Because we put limits on it.
We put limits on it. Now, with the limits on it, we've also limited things with our functions. Do you remember what it takes to have a good wave function? Continuous. What was it? Finite. There's one other one that's nice.
Can't stack on itself.
That's single valued. And smooth. So continuous, finite, single value, and smooth. These functions all fit that inside the box. Now the question becomes, well, what happens at the edges of the box? If the particle can't escape outside of the box, what's the value of the wave function outside the box? 0. Yeah. So if we are restricted inside the box, up there. I don't know why I like switching colors so much. If we're restricted inside the box, psi of 0 has to be equal to 0. Psi of L, the other side of the box, has to be equal to 0. That's to make it continuous. Since we know the particle value is 0 outside of the box, it has to be 0 at the edge of the box to make it continuous, so we don't have weird jumps. So we've got some restriction on our function. We got to pick a function to try this with. I'm going to pick a different function because I know how this is going to go. So instead of picking e to the ikx, this time I'm going to try. That's not how you write try. Psi of x equals to sine k of x. And I picked this one for some particular reasons. It just comes out easier. If we do cosine, we run into all kinds of issues. If we do e to the ikx, the equations we solve just end up more complicated. We could still do it. It's just more complicated. I know this function works out easier. And then I'll show you the math for how all of these things relate to each other. So I'm going to try sine kx. And I'm going to check the first edge. So if I check the boundary condition at the first edge, I've got to have sine of 0 equal to 0. Is that true? Yeah. Great. Notice cosine of 0 does not equal 0. That would have not. right? If we tried to use cosine of 0, we would have ran into trouble right there. As soon as we tried cosine, if we tried cosine of 0, that first boundary is not equal to 0. We'd have to do some phasing of cosine to essentially turn it into sine. So it's just easier to do sine, right? Quick check. Do you know how cosine and sine relate to each other? Add a pi over 2 to the phase? Or is it a pi? Add pi to the phase. Right, so cosine, is it pi? It's pi over 2. Okay, I was right the first time. Yeah. Okay, so that's the first edge. I happened to pick a function where the first edge works out. That's part of why I picked sine. I knew it was going to work. If we did e to the ikx, would have been a little bit more difficult, wouldn't have worked. We would have had to pick some other function. Sine just happens to work. Then we check the far edge. And this is where things, in my opinion, start to get really cool. So at the far edge, we have sine of k times L is equal to 0. How is that possible? Let me ask you something. When is sine equal to 0? I heard pi. What else? 2 pi?
Negative pi.
Negative pi works too, but 3 pi, 4 pi, right? This works generally whenever we have some n value of pi. Any n value of pi is going to work. So that means if I put a restriction of KL equals n pi, right? I put a restriction on that KL where it has to be equal to n pi. That's going to guarantee at that far edge, my function always goes to 0, and I'm going to have a continuous function. I can rearrange this a little bit, and I can say k is equal to n pi over L. At first glance, this is kind of boring, but remember, k is related to something real. K is related to the energy. So when we do this, we end up putting a restriction on the energy. So k is equal to the square root of 2me over h bar squared, and k is equal to n pi over L. I put these things together. N pi over L is equal to the square root 2me on h bar squared. We'll often just square both sides to make it a little bit easier. N squared pi squared over L squared. I'm going to go ahead and rearrange this a little bit more. We end up with an h bar squared over 2m is equal to e. Why is this so cool? Why am I so excited by this? I didn't force anything to be quantized. I didn't say I only want specific values of energy to be possible. I just said, hey, let's trap our system in a box. By trapping our system in a box, naturally fell out the idea that only certain values of energy are allowed. So I need n to be 1, 2, 3, 4, 5, 6. There's certain values of energy that are allowed. Other values of energy are not allowed. Naturally falls out. Didn't have to do anything weird besides trap it in a particular space. Quantization just comes out of this. We can rewrite our wave function now with this definition of k. We can rewrite our wave function as having n possible wave functions sine. Right? I've got n possible wave functions where n could be equal to 1, 2, 3, 4, 5, 6, 7, so on, so forth, so on, so forth. I've got a lot of different possible functions. I've got an infinite number of possibilities, but each one is a discrete energy. Not any energy, even though I've got an infinite possibilities, each one has an energy step associated with it and not energies in between those spots. Pretty weird. Pretty cool. So, we now have a wave function. This wave function, we can start doing stuff with it. Now, if you go back and read, 7b now, it uses these functions for doing your normalization examples, for doing your orthogonality examples. It uses sine n pi x over L examples, and it doesn't tell you why. It just says, hey, use these functions. The reason we're using these functions is because those are the answers to the particle in a box problem, right? It's using, and that's the problem they do in 7D. It's using the first problem we do in quantum mechanics to say, let's just play with these wave functions. I'm not telling you where they come from. This is where they come from. Now we can play with these wave functions and do things like figure out what the normalization is. We can show that they're orthogonal to each other. We should already know that they're orthogonal to each other. Why? Hamiltonian's a Hermitian operator. Eigenfunctions of a Hermitian operator are orthogonal to each other. So we already know if we do psi of 1 and psi of 2, that integral is going to be 0. If we do psi of 2 and psi of 3, that integral is going to be 0. Because these functions are, they should be orthogonal to each other because this is a Hermitian operator. And these are solutions to an eigenvalue problem of a Hermitian operator. Lots of vocabulary today, right? Lots of weird vocabulary. Hermitian, eigenvalue, eigenfunction, operators, lots of vocabulary. But it's all to kind of, it's just framing this so we have like a really consistent way to talk about this. Okay, can I tell you something weird? This is the weird part. How many functions do we have here? N, right? N functions. How many orthogonal vectors do we have? N orthogonal vectors. What dimensional space would that be? It's not really space, but we've got essentially, when we want to start decomposing our problems, we can just decompose it onto n orthogonal vectors, right? So this whole example, and this is the what I call it, the classical analogy paradox, or what did I call it? Delusion. The classical analogy delusion. This is where that classical analogy of Cartesian coordinates, like your x and your y, kind of falls apart because we've got an n number of orthogonal vectors to decompose our problem into now. It's not really like an x, y, z. It's just a bunch of vectors that don't line up with each other. It's really weird. We've only got 5 minutes left, so I should let you ask questions. If you have questions. If not, I'm going to set one. I'm not going to solve a problem. I'm going to set a problem up for you if we've got time. Question.
What is K?
K is 2me over h bar squared. It's this energy. It's all of these constants and the energy. I just use K for a constant because it makes my differential equations look easier to solve to me. Right? I don't know why I didn't write it down again. Here, let me write it down again. Right? For me, it's easier to solve. Like this equation with all of those numbers there, it looks like a mess to me. But if I just have d by d squared by psi of x equals negative k squared psi of x. That's just easier for me to think about. So k is just a placeholder for 2me over h bar squared. That's it. Question?
When you say like first edge, what do you mean?
First edge is this 0 part.
Oh, okay, yeah.
And then that's the far edge.
And the reason why you just want it to be 0 because it's at 0?
I want it to be 0 because I know out here, outside of the box, there's no wave function.
Okay. And that's why like cosine wouldn't work. But also, with e to the 0, that would just be 1, so that wouldn't work either?
That wouldn't work either.
Okay.
Now, there's so many things I want to do still. But all questions first. Question here, there, and then there.
What do you mean, like, I'm just confused what you mean by there's like n number of vectors, but then they're all orthogonal.
Yeah, you can't picture it. I mean, we're used to thinking of things being 90 degrees from each other.
Two
For-
vectors that are always orthogonal?
No, it's n different vectors that never overlap with each other. Right? So it's with what we usually do with like vector math and like what we're used to with three-dimensional space, having n orthogonal vectors, it's just like our brains can't do it. But we've got n orthogonal vectors. For us, what this is going to mean, the place where we're going to use this is whenever we have an integral So the thing that we're going to use that for is we're going to use it to simplify a bunch of our integrals. A bunch of our integrals, if we've got different functions that are orthogonal functions, we know those integrals are going to be 0. So there's going to be this nice kind of like shortcut we're going to use. That's how we're going to use this idea of orthogonality. But it also does mean we can take problems and we can decompose it into n different directions. Directions is a bad way to put it, right? We can put it into n different functions and treat it as n different problems. Question there. Yeah.
Can you restate like what you're saying with the eigenfunction relating to the Hamiltonian?
Yes. So the Schrödinger equation is an eigenfunction problem of the Hamiltonian operator. That is to say, an operator acting on a function returns a value times the same function again. That's the definition of an eigenvalue problem. From postulate 2, we kind of end up with this being necessary. Like the postulate 2 and postulate 3 kind of put together give us the restrictions on our operators and then the restrictions on our possible values. Our possible values are going to follow an eigenvalue problem. So this is the Schrödinger equation, which says if we've got a Hamiltonian operating on a wave function, we're going to get energy values out and that wave function back. So when we start looking at this, we haven't calculated the energies for a particular psi yet, but I'm going to tell you it's going to be this thing because we used the Schrödinger equation to define our wave functions. We've kind of already solved for the energy possible values. Does that make sense?
I think I need to example it.
Yeah. Question back there, and then I'll loop back around over here.
Could we get like the n number of orthogonal vectors if it was a free particle, or is it only for particles?
No, when we get a free particle, we can get a bunch of different answers, but it's by making linear combinations of the solutions. That's the free particle by itself isn't a realistic problem. That's where we either do this restrict the space or change the possible function to be a wave packet, a combination of lots of sines and cosines. So for a free particle, we really don't get that same thing. If we change the functions we're using for the free particle, yeah, we can get that. Question up here? Yeah, and then there.
Oh, you can go first. Okay, I'll go first. So earlier we found momentum, right? And we were able to do that fine. And then only once we defined the space, like a restricted space, we could find the position. No, break Heisenberg's uncertainty principle?
Not yet.
Okay.
Right, so we haven't found, for this function, we haven't found the position ortho momentum yet. And if you look at this, if we have an x sine of this is still not an eigenfunction of the position. So we can't find the specific position values. We can find an average position, and we can find an average momentum, and we can find the specific momentum value. Well, actually with this function, this isn't even an eigenfunction of momentum. Because if you take the derivative of sine, you get cosine.
Yeah.
Oh, give me just a moment longer. I know we're at time, but I just want to make sure I get the last question real quick. You have to go. Sorry, that's okay. But quietly.
You answered it.
Oh, that was the answer to the question. So what we'll do next time, please, if you can, now that we've got this idea, read through B and C. On Tuesday, we'll start on 7D. Well, this is already part of 7D, but we'll actually use these functions. We'll find position, we'll find momentum, we'll find energy. We'll actually start solving for some values.